Just water today. Hey, it's been a while. Today I'm gonna be talking about like reasoning about data structures as code, which is almost the opposite of the code as data thing. It's mostly about like sharing some of the most useful mental models that I know of. They are mostly techniques. It's not anything concrete, but it's ways of thinking about especially data, memory, and whatnot. There is also a related topic after the end, so if you have infinite spare time, go for it. Code as data is, when people talk about it, they're mostly Lisp people talking about homoiconicity, I think it's how you pronounce it. But code is definitely data, okay? That's true. Just think about this. It is in the memory of your computer, right? And it can be manipulated somehow, so it must be data. But today I'm not going to be talking about like either coding a code as a string or as an AST, but as coding code as a way of embedding data structures and reasoning about those embedded data structures. And also in general, just thinking about data in a high level way. Keeping in mind here, I'm going to be using data as not code, okay? And code means, functions, function application, stuff that does stuff. While data is mostly stuff that does not do stuff. It's just static, okay? So code, dynamic, data, static. First, for that, we need a language. We always need a language. I'm a language engineer, so I need to make languages. The language that I'm going to be using today is this. It has variables. It has let. I'm calling them arrays or tuples. And, we have a way of accessing those. And there is also numbers. An example of program here would be x0, y1, and then z, x, y1, and then z. And you can see that, x is going to be 0 because it's declared, y is going to be 1. And so that's kind of how we're going to go. There is no functions for now. So this language only has data. It's a data language, not a function language. And I'm going to be using Rust blocks, but this is not Rust. The reason is mostly because of the amazing syntax highlighting. So to start, let's start with the linked list. The linked list is one of the best data structures. It is a recursive data structure with indirections. And here, you can see kind of the same linked list. So if I open this, you can see that it's 12, 19, 37, and then new. Here, sadly, it's reversed because of lexical scoping. But you can see 12 points to 19, 19 points to 37, 37 points to new. 12, 19, 37, no. The main insight from this bit is that let models in directions. What does that mean is that every arrow here is referenced by a variable, and the existence of the cell itself is modeled by a let. So, this is a cell, which is the same as this cell. This is another cell, which is the same as this, and so on. I'm going to be using, you can think about variables here are as absolute pointers, so like just direct pointers. This is also a very common design for linked list in practice. You can see that no is actually like a reserved variable. It's just a reserved pointer. It's nothing special. And here I'm using, an empty tuple to mean it. But even if I go and erase it, it's still the same stuff, because what matters for new is not the content of new, but the existence of new. Node is a pair, and new is a reserved pointer. One of the things is that the whole code here, you can see that it points to a single node. You can call this the entry point, but we really do not care about the entry point. N12 here is the entry point, which means you point to this. I could actually be pointing to N99, right? It could be the first element. And so for that, I'm going to invoke a technique from contextual rewriting. What we call a context is pretty much any term with a hole in it. And here I'm using a small example. You can see that this language only has pair, let, and it only has one hole. So any context has only one hole because only one of the sides can be a hole. So for example, either this is a context or and this is a term, or this is a term and this is a context. Just think as whenever you get any program described by the language, any term, you can just remove one element and put a hole in it. Just one for now. That's very important. And so an example is that you can plug it, and one of the things is that you can plug it back, which is just saying replace the hole by the content. So for example, here I can say that the context is this, which is a valid program, but it has one hole. So it's not a valid program, but it's a valid context. C plugged with A means that it's that replaced by A, and it's literally that. C plugged with B is that replaced by B. But notice that now I can talk about, not about the whole program, but I can talk about like the program in different places. In this case, A and B in different contexts, and that's kind of why it's called context. And this is mostly a meta tool. This does not exist in the language. This is just a way for us to say, hey, you can do some stuff. But the context that I'm going to be using right now is actually a special instance of the context. It's an environment. The environment is just a context where it's a sequence of lets. So it's like let, and at the end, it has a hole in it. An example is this, a let followed by a hole. And when you plug it back, you get this. The same here. The environment is a null. You know, there's two lets, null and n37, and a hole at the end. The nice thing about this is that now I can talk about either null or n37 by, you know, saying in this environment, I want null or I want n37, and this becomes the last step. The environment is kind of like the whole program heap if done correctly, okay? So you can think about this as like all the nodes that exist in the system, not only the nodes of your specific linked list, but nodes of other linked lists are gonna be like floating in this graph-like space. In general, here it's gonna make a DAG. And you can say, by saying which variable, you can choose between like, what is the data that you want to talk about? And so here, null, and here, n37. In general, I'm gonna be omitting the whole of the environment. So whenever you see this, you can think about it as the same as this. You know, this is the same. I just do not put the whole. But this is a very useful technique. It's used in like all sorts of problems. And I'm gonna be using here, but just keep in mind, this is the part of the language that we're using mostly. And the programs are going to be inside of the lets. Another example is that you can, because of the lets, you can do sharing. Okay, you can pretty much you have a bunch of nodes, and there is you have a bunch of lists, because remember, in a linked list, each node is a linked list. But you can actually point two different lists to the same node. So for example, here I added n25, which is 25 pointing to n99, and n17, which is 17 pointing to n37. I'm gonna show the graph on Krita. I think it's this. So remember, we had 12, 19, 37. That's the initial one here. And now I have 25 pointing to 99 and 17 pointing to 37. This is why the let is kind of like one of the most important things, because sharing is kind of the core of those recursive data structures. Like being able to just in a single operation, imagine that you have this program, right? If I want to add a node and to like make a bigger list or like to duplicate the list, I just go and add a cons, you know. So in two operations, I made like two more copies of the list. But notice that I didn't copy. I just say, hey, here's a new node. And when you want the rest of the list, you go to n99 or n37. You can also inline it back. So let's say, you know, we had this, we selected n17. We can remove all the unused nodes. And now you get this. And if you inline it back, you're going to get this, which, you know, it appears like a linked list, which that's what we're modeling. Notice that I didn't need to talk about pointers. Well, I said that variables are pointers, so you can think about them as pointers. But I didn't need to like invoke the concept of a pointer as a number. Or I didn't need to invoke the notion of mutation in any meaningful way here, even though I could. I just said, hey, I can point to new things. I have a series of lets. Whenever I want a specific instance of the list, I have the variable, and by knowing the variable, I know which chunk of the list I want, and I can actually go and reason about that. One of the reasons why this kind of model is useful, in my opinion, is because we can reason about memory. And in general, reasoning about memory is hard, okay? Because you need to actually know the intricacies of your language and whatnot. In general, what you actually need to know is you need to know the model of the language, which here I'm going to be using a thing called the uniform memory model. Languages like OCaml, JavaScript, Python use it to some extent because they are practical models for GC collected languages. And the main thing about that model is that everything is either a variable, aka a pointer, a number, or a tuple. Okay, and the tuples are going to be laid flat. The variables are going to just be a pointer, so it's constant size, and the numbers are also a fixed size. So let's say this is a 64 bits platform. Each one of those is going to use one word, aka 64 bits, and each tuple, like if the tuple is a pair, it has it uses 128 bits. So a good proxy for this is that how much memory you're using is the sum of the size of all tuples. In this case, all the tuples are of size 2, and I have 5, which means that would be 10. One of the things that you can notice is that if I inline everything, if I erase the sharing, the memory actually increases to 16. So by like doing inlining of everything, instead of like reducing the amount of memory that I'm using, I'm actually using more memory. And this does have some advantages, but just keep that in mind. Sharing is the best tool to actually compress time and space. It's kind of the general tool in general. And whenever I say sharing, you can think about it as indirections, but here there is a reason why I'm using sharing. So yeah, inlining increment the amount of memory. We can now go to trees. So, we went to linked lists, which are very simple. You guys know how they work and whatnot. We can also do trees, general trees. This is the same as this. Let me actually open a tab here. Okay. So if I open here, you can see that this is the same as this. I'm doing, because lexicoscoping, it's reverse. So this is the first line. Those three are the first line. Then those are the last line, -1, and this is this, and this is this. We can check going from the root, which is n2. I can go to the value is 2. I go to n7, and 7 points to 2, then n6, 2, then n6. 6 points to 5 and 11, 5 and 11. 5 out, the other 5, I didn't notice there is 2 5s. The other 5 points to 9, and 9 points to 4, and the 2 points to 9, and 7, and then 5. So you can see that it's kind of the same. You just model it on your head using the variables instead of using variables and lets instead of like playing with it. In fact, like I've been using this type of model for so long that I'm actually, for me, this is way easier to visualize with this because traditionally, I work using programming languages and doing programming languages, and my brain kind of know how a programming language works. But a graph like this, sure, you can imagine moving the bubbles and whatnot, but I don't know, like, if I want to move this, I just do this. And you can see that it didn't change anything because let's commute. So things like that are part of the tools to use to reason about data structures using languages. Here, the first element is the value. The rest is the reference. And yeah. Another thing that you can do instead of just a tree, the tree case is quite similar to a linked list. It's just that, it's if you know the linked list shared, It's just the opposite. Instead of having 2 pointers to everything, one thing may point to 2. Now, we also have the notion of a DAG. A DAG is, stronger than the linked list, stronger than a tree. But it's pretty much a tree where 2 nodes of the tree can point to the same. So not only, normally the tree you can think about, there is a node here and the node can go to the sides. So like 1 node goes to 2. Here we have the opposite. 2 nodes goes to 1. I don't know if I did that graph. Oh yeah. So what was this again? This is a DAG. Yeah, this is a DAG. Okay, I remember now. This is a DAG. The reason for that is that N7 points to N10 and N5 and N11. But N6 and N7 also points to N6, N5, and N11. So you can see that I first open and then I close. In terms of graphs, if you go here, this should be this. So, 7 to 10 to 6. And you can see that now they have this crossing because both 10 and 11 points to the same thing. Here, it doesn't look like this is a DAG because these numbers are not, there is no sharing. But if you think that those could do this, it may help you to see it. So like pointing to the same. You can also do the inlining of the DAG. So like you expand the DAG, eliminating the sharing, and that just becomes a tree. This is just a normal tree. Notice that I just duplicated those nodes, and now they're pointing to individual nodes. Again, it uses more memory, but it's just a tree. One of the good properties about that is that you can see that if you want to traverse a DAG, if you have something like this, you can treat it as a tree. You just go down because it's directed. You're never going to go up. There is just one missing type of interaction, which is maybe the trickiest one and the one that everyone struggles that way more, which is cycles and graphs. Graphs are annoying, mostly because they may point to themselves. And here we're going with directed graphs because that's what computer scientists use the most. The problem with a directed graph is that there is no lexical scoping solution. You're going to need something like hoisting. Pretty much you need a recursive let. Here I'm just using hoisting. But it's the same idea. A is now pointing to A, B points to B, A points to B, B points to C, C points to A, and C points to B. That's it. You can see the diagram here. A goes to A and B, B goes to C, and C goes to A and B. So this is just like just a graph. Still the same model. Lets are indirections. I draw the lines, I draw the bubbles with the lines, and that's about it. Again, there is some real advantage here because this is just code. You can, if you know how code works, you're going to be able to follow this. This is not a real language, of course, but to some extent, most languages are going to be able to represent things like this. An advantage of like hoisting in general is that you don't need to use lexical order, and it's just nicer. So often I just use hoisting implicitly, even though it has way more power, just to avoid like needing to draw my stuff in reverse. But what are the limits about this model? This is a model. You can use this to reason. This is not real code. This does not run on a CPU. You could, but there is no good reason. This is just a model that you can apply to many other languages. The reason why, the good thing about that model is that it's kind of a universal model to some extent. Any language, no matter if you're doing C, it doesn't matter actually if you're doing assembly for that matter, you're going to have those structures. You're going to need to reason about them in some ways. You're going to have indirections, right? You're going to have something that that you need to go to memory to access, and it's kind of like a pointer. Well, that's literally what it is. And most of the time, you don't need to mess with pointer arithmetic. And pointer arithmetic is more or less pointer compression to some extent. So it's like, you want something that you can think about that in a high-level way, and then later you can start, shaving off bytes used by memory, doing pointer arithmetic, or you can compress stuff, making stuff flat, like using arrays and whatnot. Those are limits of this model. This model does not give you flat memory in general besides of simple arrays, which here they're actually tuples because they're static. You can have better models. You can go and make a model that tracks how much memory it's going to be used like concretely a model that handles unboxing. I think my previous video handles unboxing to some extent, but kind of like, it's the true thing of like no model is perfect, but some models are more useful than others, right? This is a very useful model. And as you remove details of a model, it tends to be more useful because now you can apply it to more scenarios. Of course, it also means that it's more wrong. It's less correct because it is not mapping as many of the details. But this is pretty good. You can go and you can, if this was OCaml, well, if you translate this in OCaml, you actually know that this is how many words are going to be used. So you multiply it by the word size, which is 32 or 64 bits, and you're going to get how many bits your program is using. If this is JavaScript, and that's more complex because there is some implicit information and whatnot. But for OCaml, this is pretty good because OCaml is simpler in that sense. Now, part of the problem here is that I'm not going to be able to give this to you in a context, right? I'm not going to be able to give this to you on how do you think about creating those structures. How do they actually work in, whenever you have code, aka functions and things like that. But you can kind of see that at least the static view, where it's not computing anything, you can use that to reason. And you can also use that especially to reason about space complexity. One of the things that you need is that you also need the time complexity, right? Thinking about it in terms of computing. With that, you would be able to reason about complete programs, but it's so much more work to reason about time and space at the same time. This example is going to be on GitHub. And this is mostly it for today. So, bye. Okay. I need to drink some water. Oh, you can follow me here on YouTube and also on Twitch. You should also probably come back in like 15 seconds. It's good to drink some water. By the way, I've been going to the gym. Good stuff. Highly recommend. Is it been 15 seconds or something? I don't know, man. Well, by the way, I'm having a lot of progress in my language. So if you follow me on Twitch, feel free to ask questions. Okay, now that, only the most masculine and straight men are left, let's talk about time a bit. The other topic of this is, this was about space. Now we're going to go to time or data and code. You choose your words. This is where we're going to, go very much outside of the scope that I'm expecting people to get. So now we need a model of computing. And as always, we start by making another language. Here the language is going to be this. This language has only lets numbers, but it has addition. This is a bit better than the previous one. And one of the things that I didn't get into details in the data section is that how does the language compute, right? That in general is given by rewriting rules or rewriting rules. Those two are the ones that we're gonna go first. And pretty much what this is doing is whenever you see n plus m, like the numbers, actually the numbers, not a piece of code, you just do n plus m. So you just actually do addition. So if you see like 5 plus 6, you transform it into 11. The same goes here for the let. Whenever you see a let, you just do substitution. Okay, you find all the variables and you replace it by the thing. The model that I'm going to be using of computing here, it's not about instructions, it's about reductions. Reductions are a bit more high level. You can also think about instructions in terms of reductions. And this does not always work because you need to be careful about your reductions to know that the reductions actually map to something that is meaningful in terms of performance. We're going to get into that. So the model of performance here is going to be reductions, and yeah, at this time I do have a guideline. That's why I'm looking to the side too much. I don't know how to. I need a teleprompter. Do the substitutions. Oh, one of the important things about this is that this can be fired, so you can do those in any order. Like, you do not care if you're going to do like left to right, right to left. This system works anyway, but the main thing that I want you to get is that there is a performance implication of that. So even though this system does not care which order you're going to run, so if I start with this example, x equals 1 plus 2 and a bunch of x, I can do first addition. So I do addition, reducing this to 1 plus 2, and then I do substitution, replacing all the variables by 3, and then addition again, and I get 9. So you can see that here, well, this is not addition. Here it was done in 3 steps. I can also start by doing substitution first. This is as valid. So I do 1 plus 2 plus 1 plus 2 plus 1 plus 2. The problem of this is that if you look at how many reductions I'm going to need, so this is 3 and the other one is 5. It's actually worse than I expected. Here I need 5 reductions. Here I need 3 reductions. If we say that a reduction is 1 second, we're going to take 3 seconds to run using this strategy and 5 seconds to run using this strategy. We call those kind of strategies, the order that you're going to run stuff. What is your normalization strategy? Like, how do you normalize? Think about this as a game. Like, how do you, what is the strategy that you're going to do to play the game? And think about this as like, if this was a good model, and in this case it is, so, but for this limited one, if this was a good model, that means that the strategy that does less reductions is the best. Okay, so that's the game. You win if you do that. That's if it is a good model. It's not, this one is, the next one is not. So let's go to, a bit more concrete language. Remember that I was talking no functions, now we have functions. This is the lambda calculus plus let. It still has the numbers. And this one specifically, it's a subset of, so I mentioned space and time. This is the substitution calculus, which is the lambda calculus plus let, and the reductions are done like that. Okay, the main one is that compared to the normal lambda calculus, the beta is at a distance, which is a special thing. It's very important. It's cool stuff. We're gonna also need the environment again. This time the environment is marked by L. Why is L? I don't know, man. It's just a standard that they use. I'm just following, the tradition. So, how does this work? Let's get this example. You have a function, 2 lambdas nested, and you have 2 arguments. Why do I say that it's at a distance? Because after you do the first beta, look at where the x is. The x is on the left-hand side, which means that this is not a lambda, which normally this will not allow you to do a beta, so you would be forced to do a substitution. The main trick of this is that I have an L here. I'm saying that I may have an environment in between, the function and the arguments, which means that here I can actually go and do this. So this is a beta at a distance, and that's the main rule. The main difference between this and the traditional beta. You see that L is in between the function and the application, which in this case, the L is x of m, and you can see it here. But part of the magic for me is that first you can define this using just normal syntax, but the other rules are mostly normal. This is also needed for some other properties. You may say, why not just do the normal beta and just force to do substitution and whatnot? It is slower. This is actually way better in practice. This also shows, why this is a bad model. The cost of each reduction is different. For example, if I say that every reduction is, it costs 1 second, addition is much simpler than substitution, for example, or not. It depends. In practice, it is. Addition is simpler than substitution. So saying that both of them take the same time is just false. And it's actually worse than that because the cost of the same reduction is also different. So for example, a beta may cost more than, one beta may cost more than another beta. And here you can see why. Because for example, a beta is cheaper, if you just think about it, than a beta at a distance. Because a beta at the distance, I need to do 2 things. I need to transform the thing, move to the left and whatnot. And I also need to move the substitutions outside. So I need to do those two transformations, which it's described by a single rule. But this model is still useful, okay? Just keep in mind, it's not perfect. It's not going to give you like how many cycles it's going to take on a real CPU, but it is useful. Sadly, the real world, it's a bit more complex than just counting reductions. Or is it? We can actually just make a better system where this is going to work better. One that is really good is the value substitution calculus by the same guy on the same paper. This is almost becoming paper review. The value substitution calculus says that substitutions can only happen if the thing is a value. Okay, and the value it's the same term, it's the same environment, but the value is a subset of the terms. It's either a number, a variable, or a function. It can never be like, for example, fx is not a value. It also has the environment, and the environment is moved from x to the outside. And this actually works, and it's one of the stupidest things. But keep in mind, this does work, okay? This also actually matches how real languages work to some extent. The beta to distance is still the same. The only difference here is the substitution. It's weird, but it's work. Oh, keep in mind, this is a restriction. You can see that this is just strictly weaker than the substitution calculus. But because it's weaker, it has some better properties. One of them is that it's reasonable in most of the forms, especially if you limit it to the weak form, which is this. It's reasonable both for time and space. And reasonable here just means you can actually count the reductions, and you're gonna know how much time and how much space is it's gonna work. So because it's reasonable for both. In the weak form, which is a stronger restriction than this. In the strong form, you can do it, and if you look here, it's still reasonable. It's kind of weird, but you can still use that, okay, to reason about. So if you have you may have two options to run the program. One example is that, for example, you could have x and y 3 plus 4. I still have two options here, right? I can either do x or y, but I cannot do this substitution anymore. And the reason why I cannot do this substitution anymore is because this is not a value. So remember that slow path that we had available on the beginning? This one? We do not have it available anymore. And because of that, the cost of each reduction it's a bit more uniform. So if you amortize it, you can actually use it to reason about the actual performance of the program. Notice that it still allows you to have some, it still gives you freedom. You can actually go from here to either 3, or you can actually go to 7. And but you can see that it has one nicer property, which is it's easy to see that it's confluent. Well, the original one was also confluent, but it goes to the same result. So this is one property. But this is kind of like, if you're not doing theory and whatnot, you should probably just use the value substitution calculus. There is some work on it. It's more or less a standard. It's really good stuff, okay? But there is another system. It's one of the favorite of mine, and it's a basis for probably my next video, but maybe not. It's another video, and it's a great model on paper. And on paper, I don't mean on paper as in in theory. I mean on paper whenever you're doing reductions on paper, whenever you're like transforming it on paper. And on paper here, I mean in a markdown, because I don't know how to write, so I only use markdown. And it's the linear substitution calculus. The linear substitution calculus, it's actually from the same paper. The name of the paper, by the way, is an abstract factorization something, which is this. And this has two rules that are different. We're gonna go through them. I really like it. It's a bit more flexible in some senses. Is my context wrong? The context here is wrong. This should be, let me update in real time, This is live coding now. And C plus N plus C, okay. Again, the context is still just a term with a hole. We need actually the context now. We don't need only the environment. And the reason for that is that addition is still the same. Beta at the distance is still the same. But now we have linear substitution and garbage collection. Okay. Linear substitution is a substitution that is linear. It does one at a time. Okay. And garbage collection does garbage collection. It takes, it takes a let that is not used and it removes the let. And this is just saying you can remove it if x is not a free variable in K. So if x is not used anymore, you can do garbage collection. The linear substitution one has the context here, and the main reason is to say that we ignore the stuff in between. Okay, we just, instead of going from there may be some stuff in the middle, we can just keep it. The only thing that matters is that we can do the substitution like that, and you can see it here. X equals 1 y of x, and I can go and I say that this is the context that I'm looking. So this is the stuff in between my let and my variable. And I do the substitution, and that's it. And this is the same as doing this. If you just, it's the same as get the variable and replace it by this. It's just a way of saying whenever, any place that you look, you can go and do one substitution. This is kind of like how I would run the program on paper anyway. I think garbage is, it's with an A, yeah. And garbage collection happens after, okay? The reason why this is called garbage collection is because this actually allows you to model garbage collection in practice. Because one of the things that you can do here is that you can actually delay garbage collection. So you can do all the substitutions, and then when you go back, you collect all of them instead of doing the substitution of x and then collecting x, doing the substitution of y and then collecting y. Delaying collection, super important. Let me show, an example. Let's say this. This has a bit that is useless. This y here, completely useless. And this x, x 1 plus 2. So let's first do addition. So x 1 plus 2 goes to 3. And this is the state transition that does not exist on the other systems. I cannot go and transform just one variable. If you go to the value substitution calculus, all the variables go away as soon as you do the substitution. You can see that the x completely disappears here. Okay. So in this system, I can do one variable at a time. And then I can do the additions. And after I finish everything, now I just do all the garbage collections. So if you think about a real, functional language, this is kind of like how it works in practice to some extent. There is some other restrictions, namely the evaluation order that is going to happen. For example, in something like OCaml, it's still called by value. So this cannot be anything. This needs to be a value, which is a valid restriction, by the way. Well, you need to do some other stuff, but in general, that is more or less a value, a valid restriction. And I'm mostly going through this to have, how to point people to some content on this. In the next video, I'm going to be using this a lot. And I actually use this a lot because by far it's the most natural on paper. Whenever I'm doing stuff, I don't care about the order. Oh, a detail that I forgot. Notice that I don't need to do the substitution. Because this y is irrelevant, I can just skip it. So I don't do x substitution. I could go here and, do this, for example. This would not be a problem. But I don't. I just garbage collect. So I'm doing less work. This system by itself is not reasonable. So you cannot just count the number of substitutions. There is a lot of work on it. Some extensions in a lot of other stuff. It's just good stuff. It also has a nice relationship to proofnet, which is this. It's another paper by Akatoli. It's a I don't know how to pronounce his name. He's a pretty cool guy. But yeah, that's kind of it. So one of the problems is, which one do you use? Like, what is the context, right? In which context do I use each one of them? How do I think about them? How do I think about time and space together? This is mostly kind of the stuff that you need to play to, you put both of them, both the techniques for data and the techniques for code together. And now you have a model of thinking about code, like kind of on paper, dynamically. And keep in mind, this is also at least for me, it's way better to run this on my mind than to run, if I try to run a Turing machine by hand. It's just so much more work. This is more natural. It's more high level. And which one to use really depends on like what are you doing. Are you just implementing an eager language? The value substitution calculus is probably good enough. Are you actually studying different stuff? Maybe you want strong evaluation, maybe you don't. Things like that, you know, maybe you want to reason about garbage collection. Maybe you're like, yeah, garbage collection is implicit, it's given by the system. It really depends. How granular do you want to reason about that? You know, each one of them prevents different techniques. For example, you can actually make the value substitution calculus with linear substitution. And it's going to have some different properties. And in fact, probably that's what I do by hand. But you don't need to, right? If you're studying, for example, how a lazy language works, can you use the value substitution calculus? Actually, yeah. If you go to something like Haskell, what Haskell is saying is that it's just restricting the order, but it still fits inside of the value substitution calculus because it's a good system. It's a good system, sir. They are mostly techniques. You know, you mix them together, you use them to think. You play with each one of them. You know that when you do some of them, you get some properties. The bet at a distance one, for example, is super important if you're doing a theorem prover, because otherwise that getting stuck bit that we get there, what was it? Here. Otherwise you're going to get stuck here and you're going to need to do some other stuff. A lot of this comes from the explicit substitution tradition. So if you go to check out work by Delia Kestner, she's insane. And Akatoli, you know, Akatoli Beniamino Akatoli. Both of them have like amazing, you know, they have a shit ton of stuff. You can just go check their work, but it's mostly like techniques to think in terms of first principles. And I think that's it for today. Do I have anything? I don't know, let me think. Yeah, no. Hey, yeah, follow me on places, Twitter, you know, X, YouTube, Twitch. It's probably going to be below. This example is also going to be on the GitHub below. And yeah, that's it. Bye.